there was no small t. Okay, the equations that we derived that had small t, but the numericals that we solved in chapter 2, they were steady state. Okay, chapter 2 we started including small t. Okay, and we started solving equation. Chapter 4 has 4 parts. So part 1 was lump system analysis, right? So in chapter 4, in transient heat transfer, we have two types of bodies. First body is a lump system in which the temperature changes in the body, but it stays same at every point. Okay, I'm going to revise the chapter 4. So in chapter 4 we have two types of system. One is lump system in which the temperature changes with time but it stays same at every position. Okay. The body 2 is a non-lump system in which the temperature changes with time as well as position in the system. Okay. So this copper ball was an example of a lump system and this was a non-lump system. So we had two types of bodies. Okay. Then we derived the equation for lump system analysis. Alright. And in order to check if your system is a lump system or not, the first thing that we were doing was we were calculating Biot number. Right. So if the Biot number was less than equal to 0.1, that means the body was a lump system, otherwise it was a non-lump system. So this thing we do whenever we solving any numerical, first thing we check is if that system is a lump system or not. Okay, so we calculate the Biot number. When the Biot number is greater than 0.1, when the system is not a lump system, then we had to derive equations, right? So we derived equations for again a plane wall, a cylinder and a sphere. So we saw that the equations in heat transfer in transient mode when we were deriving, they were very complicated. So we had to non-dimensionalize, right? We non-dimensionalized in our last class. And we had some values. These values were these: dimensionalized space variable, dimensionalized temperature, dimensionalized time, and Biot number. Okay, so we were non-dimensionalizing our equations. Then we had two types of solutions for a non-lump system. First is using the equation, which is an exact solution, right? So we have three equations for a plane wall, for a cylinder, for a sphere. So this you use when you are asked to solve the numerical by exact solution. Okay. The other method is using Hessler charts. These. Okay. Your answer will be same, but the Hessler charts are not that approximate. Okay. Not that accurate. And then, so this is where we started, right? These are the three equations for non-lump system, and these equations have some variations. When you are studying temperature, this was replaced by A1, right? Here A1, and the value of A1 and lambda 1 are given in the table in your book, right? Then the second variation was if you are asked to calculate the temperature at center, so in that case your XR becomes 0. This was your second variation. Okay, and then you have Hessler chart. So in our last class we solved this numerical, the dead body numerical, and another was this one using the only Hessler chart. Today we will start from here. Okay, this is also a numerical in the back of your book. So chapter 4. So we are going to start with this one here.
First we have to define the transfer model and we use we define the Biot number as best as we can. When it defined as a non-term, we have to find the Biot number again, right? Because
so yes, in Biot number, when you are calculating Biot number, your formula is HLC. LC is characteristic length, right? And when you are when it's a non-lump system and you are calculating Biot number to check your A1 and lambda 1 here, right? These values, right? So in this one you see your biot number is R. It changes to R. It's radius for cylinder for a sphere. Okay. L is for plane wall and R is for cylinder and sphere. This is what you were asking? Right? Yeah, this can be confusing. So when you are checking, it's a cylinder or a sphere, it becomes R. Okay, so we have a 65 kg beef. Okay, the values of the thermal conductivity of the beef diffusivity is given initially at a uniform temperature 37 degrees Celsius. The room temperature is 37 degrees Celsius. To be cooled, the temperature of the beef is 37 degrees Celsius, is to be cooled by a refrigerated air. Okay, this beef piece is in a refrigeration and the air in that refrigerator is minus 10 degrees Celsius flowing at a velocity of 1.2 meter per second. The average heat transfer coefficient between the carcass and the air is 22, treating the carcass as a cylinder of diameter 24 and height 1.4. Disregarding heat transfer from the base and top, it means heat transfer is one dimension. Determine how long. How long means they are asking time. Okay. Determine how long. Determine small t. It will take for the center temperature T0 of the carcass to drop to 4 degrees Celsius. So also determine if any part of the carcass will freeze during this process. So this beef we are assuming as a cylinder. Okay, the shape we are assuming as a cylinder. The temperature of this beef is 37 degrees Celsius. Okay, this is a refrigerator. Okay, the temperature in this room is minus 10. Okay, so and the heat transfer is by convection. Okay, at the surface, and the heat transfer coefficient by convection is 22. Heat transfer from this side and this side is negligible. Okay, so it's only in one dimension. Alright. The velocity of the air is given, heat transfer coefficient by convection is given. Okay, so first I will write whatever is given. And they are asking time. T infinity is the temperature of the okay. This is T is the velocity So the temperature will start dropping here first, right? So they are asking if the carcass freezes. This means if the temperature here goes negative or not. This is the second part, right? The first part is they are asking the time small t it takes for the center temperature to drop to 4 degrees Celsius. Initial temperature of the carcass of the bees is 37. The outside temperature of the room is -10. The temperature will drop eventually. Heat transfer is happening from bee to the outside. The temperature drops to 4 degrees Celsius. They are asking how much time it takes. Okay, and this is the cylinder. Alright, answer is also given. So first thing we do is we calculate Biot number. We want to see if the system is a lump system or not. Okay. Biot number should be less than 0.1 for lump system. When you calculate this, you will get Biot number 5.62. Okay. Biot number for cylinder we are calculating. We will write H R naught. R naught is the radius. Okay. Divided by K thermal conductivity. H is the heat transfer coefficient by convection. H is given. R naught they have given us D diameter 24 centimeter. Okay. So half is the radius in meters 0.120 divided by the thermal conductivity is given. When you solve this, the Biot number is 5.62. So it's not a lump system. Okay. So now see carefully. So this is the formula, right? This is the formula for cylinder, this one, right? So we have 2-3 variations of this formula. So now you have to understand which formula you should use. Okay. So first variation is this. Okay. Second variation, so this is the normal variation. Second variation is when the T0, when the center temperature is given. Okay. And this is the second formation, second version of the heat transfer, transient heat transfer in a cylinder. Okay, exact solution. So which one do you think we should use? This one or this one? You have just look at the given quantities, what is given in your question, and see which formula should you use. This one, I mean this one here, or this one. This one, right? Because T0 is given. In your question, T0 is given. Is the center temperature, right? You have this calculating toe here, right? So we will use this variation.
แต่ให้พี่ดูได้เลยแซวไม่ได้โอ้ไม่ต้องวิ่งเอามันไม่ได้เงิน
กูไม่ได้วิ่งเอาเงินวิ่งเอาต่อมันตกไปตัวนั้นน่ะเสียดายเนี่ยวิ่งมาถึงแล้วไงจะถึงแล้ววะ
เท่าไหร่รันเสร็จแล้ว
แบบเนี่ยดันต่อไปเนี่ยตรงเลือดอะ
เหลือๆเลย
เลือดลงไปอะ
มีบูด้วยได้เงินด้วย
Okay. We are finding out toe, non-dimensionalized time. formula you should use. Okay. First, check the lump system. If it's not a lump system, it is a cylinder. Which variation of the cylinder formula for exact solution you should be using. Now you can also check your answer from Hessler chart. If you remember from our last class, I told you the exact solution, and then you can also check the answers from Hessler chart. So maybe we can try. So this chart is for cylinder, right? This is for cylinder. We are trying to find out this in this question, right? We have 1 divided by pi. We have I of number divided by 1. And here this value also we have. We have y-axis. We have the blue lines. Tell me the value of tau. Is it same as this? 0.396. What is the value of 1 divided by y? Is also focus. Calculate this, calculate the blue lines, and check the y-axis. What is the value of 1 divided by pi? 0.177. Okay. What is the value of y-axis? Y-axis is 4 minus 10, 37 minus 10. No. Value of y-axis. Yes. 29. Then what is the value of x-axis? It is somewhere close to 0.396. Will be somewhere here, and your 1 divided by is 0.17. Okay, somewhere in this line. This line 0.1, this goes up until 0.297. So until here, okay, and then you match the x-axis. So your x-axis should be somewhere around 0.396. You can check, right? You cannot, if you use this chart, you can of course, like from the starting, you can just use this chart to obtain the value of tau. But these charts are not that accurate. Okay. So you are advised to first use the exact solution and then check your answers from the one was lump system. Okay. Second was infinite. Let me check the exact name. Second was transient heat conduction in large plane walls, long cylinder and sphere, where we use the exact solutions and Hessler charts. First was lump system analysis, where we check if the Biot number is less than 0.1, then only we use this lump system. Okay. Now third topic of this chapter is transient heat conduction in semi-infinite solid. Okay. So first we will understand what are semi-infinite solid. So sometimes you have to solve problem. Let's suppose I'm asking you to solve the heat conduction in a pipe which is buried in the ground, right? So semi-infinite bodies are bodies. Solid is an idealized body that has a single plane surface and extends to infinity in all directions. So like Earth, you can assume Earth as a semi-infinite solid body. Okay. Assumptions should be constant thermophysical properties, no internal heat generation, uniform thermal conduction, initially at a uniform temperature of Ti.
1 2 3 4 5 6 7 8 9 10 11 12 1 ใน 6ของมินเป็น1 ใน 6เท่ากับของมินได้ตัวอะไรบอกด้วยแต่ไม่ต้องอันนี้นะไม่ต้องอันนี้
Oh, we did not solve the second part. Oh, wait.
ได้ตัวบอกลักษณะมาตั้งให้ก่อน
โอ้ยกา
นะสีอะไร
สีม่วง
เฮ้ย
ดูดิ
ไม่ใช่นะโอ้เก็บไปตั้งนานแล้วมิน
ขอแล้ว
ถ้าไม่เกี่ยวเพื่อนเอาก่อน
ทำไมมันเหลือศูนย์เลยอ่ะ
ไม่เหลือศูนย์เถอะไหนว่าเพจโคตรไม่ได้สักตัวอยู่ในเชื่อ
So this question has a second part as well. Also determine if any part of the carcass will freeze during this process. Okay. So the freezing we are assuming will happen. Of course, it will happen first at the surface, right? At the surface of the carcass, it will start freezing, right? So we will check what is the temperature at the surface of the carcass.
พร้อมจะบล็อกตัว
Alright.
ปวดหัวแบบว่าให้ฉันฟังสื่อใช่ปะ
พิตาชิโร่บุกกี้พีสตาชิโร่
Now we are checking if any part of the carcass freezes. So we will assume here that the surface, let's check what is the temperature here, right? So this will become 1.1. Previous question this was 0 because the temperature at the center was given. Now let's put it at the surface. From the table semi-infinite planes, right? What are semi-infinite planes? So Earth can be assumed as semi-infinite plane. So take a picture. So semi-infinite planes. These planes, they go infinity in all directions. Alright? This direction, this direction, this direction, it goes to infinity distances. So we can assume Earth as a semi-infinite plane in comparison to when we are calculating heat transfer in a small pipe which is inside the Earth, which is beneath the Earth. In that case, the whole Earth can be assumed as semi-infinite plane. Alright? So they are one-dimensional. In this one, they are one-dimensional problems. In semi-infinite plane, the some assumptions that have been made for semi-infinite plane are they have constant thermophysical properties, they have no heat internal generation, uniform thermal conditions on its exposed surface, and initially a uniform temperature. Okay. So like Earth, again try to understand what is a semi-infinite plane. Like Earth is a semi-infinite plane if you are calculating heat transfer in a small pipe which is buried inside the Earth. Okay. You can also assume like when you get laser treatment, right? Laser treatment is like the heat transfer is happening for a microseconds. They pulse, right? They shoot the pulses for very small period of time. So in that case, your skin can be assumed as semi-infinite plane. Another example can be again, like if there is a pipe buried inside the earth, right, and it is buried only few meters from the surface of the earth, right? So in that case, in the z direction, right, the distance is infinity in comparison to the few meters, right, few meters that the pipe is buried. So in that case, this is a semi-infinite solid plane. Okay, so earth, laser treatment, anything that is very large in comparison to where you are studying the heat transfer can be assumed as a semi-infinite solid. Okay. So again now we have a semi-infinite solid and we need to derive some equations for semi-infinite solid, right? And again we will start with a differential equation, then boundary condition, then initial condition, and we do the derivation, right? Again the derivations are very complicated since it's a transient heat transfer, right? So I'm going to tell you the equations, the final equations for semi-infinite solid. But this is how you get it, okay? So this is in a one dimension, right? And there is a small t. So they use the separation of variable technique. The separation of variable technique does not work in this case. It worked in 4.2, right? But it does not work in this case since the medium is infinite. The partial differential equation can be converted into an ordinary differential equation by combining the two independent variables x and t into a single variable eta called the similarity variable. Okay. So like in 4.2, right, you had some non-dimensionalized values like tau, right, and non-dimensionalized temperature like theta. In semi-infinite solid as well, you have some non-dimensionalized quantities. Okay, first one is eta, which represent x and t. X is the distance until the heat transfer is happening, your heat transfer is penetrating, and t, small t, is the time. So combining these two is one unit called eta, okay, which is called similarity variable. This one, eta here. I will explain all of this, their physical term, okay, what do they mean in physical meaning. But these are the similarity variable, and I will explain all of this. The error function, error function of the coefficient of error function. Okay. these two values, x and t, right? This x is until infinity in our semi-infinite solid, right? So when heat penetrates any body, this is x, right? This goes until infinity. So the temperature changes, right? Temperature changes, but it changes linearly, okay, until infinity. So we have this value x, which denotes the distance until infinity, and we have small time. Small t is time, right? So this graph here will be, and this is x temperature. It is very linear. So just to minimize the variables, right? Like we did in the second part, we use this function eta. Okay, this combines both the distance and the time. Okay, that's why we are using eta. It reduces the variables. Let's understand this with some example. So let's suppose this is a wall or a surface, and the temperature inside here at several point is 20 degrees Celsius. Okay, and you started heating the surface. Let's suppose at 100 degrees Celsius, right? So it will penetrate deeper, right? Slowly as the time increases. You start here, you are giving more heat here. It's at 100 degrees Celsius now. So it will penetrate slower, right? With time, it will penetrate deeper, right? So eta tells you the actual distance from the heated source. This is the heated source. Okay. If you apply this here, position. You have two terms. This will tell you the actual distance from the heated surface, right? This will tell you the heat penetration depth. Alright? If you have this, you can determine the position. Okay, you can determine the position. Eta basically tells you the position. Alright? You are halfway through the heated region means the heat has penetrated 10 centimeter inside it. This is 10. 10 is heat penetration depth. This is heat penetration depth. And this is actual distance. Okay, you were standing here, your nail is here, or you are finding out the temperature here, and after t second the heat has penetrated here 10 centimeter. So by eta you can determine where you are in comparison to the heated region. Okay, in this case you are halfway through the heated region. Okay, again you don't have to calculate this, you have a table, but I just wanted to explain the physical meaning of eta. Okay, you can determine the position where you are or where is your nail or whatever point is in comparison to the penetration depth. Okay, heat penetration depth. Right. So you will see eta like you see theta tau in 4.2. This is your eta. Okay, this is called similarity variable, where you have combined x, which is the distance, small t is the time. Okay, together. So you are basically reducing the variables. Okay. So this is eta, right? This is called coefficient of error function. Okay. Now what is error function? Okay, first understand you will be left with 4 equations. Very easy actually. You will only in semi-infinite solid, in 4.3, which is semi-infinite solid, you will have 4 equations. Okay, 4 equation depends on what kind of problem you are solving. If your problem says that the surface temperature Ts is constant, okay, you will use this formula. If your surface is exposed to a constant heat, you have a heat flux, then you will use this formula. Okay. If there is a convection, if there is a constant wind, constant water on the surface, okay, you will use this formula. If there is energy pulse is the impulsation. Like I told you that I gave you the example of laser. When you are making the tattoo, the heat is generated in pulses, right? The heat is given in pulses. So if this is the case, if your numerical has some energy delivered in pulses, like in the tattoo, when you make the tattoos, in the laser treatment, then you will use this equation, energy pulse. So only 4 equations, okay? I will write down the equations, and then when you do numericals, you will understand better, okay? Before this, I will explain what is this term, coefficient of error. scared looking at this because most of the time this becomes 0, this becomes 0. Why? I will explain this in the table. When you calculate this, most of the time this value is very high, and for that the error function value is 0 most of the time. So you have only left with this value and maybe this part. This part becomes 0 most of the times. Okay? Again, it is a semi-infinite solid. Specified surface temperature is specified, is given. Probably they are asking you temperature at some point, at some time. You use this formula. If the heat flux is given, probably they are asking you temperature at some point. Okay? Case C will be, there are 4 cases. Convection on the surface. There is a convection on the surface. Again, semi-infinite solid is like a earth. Okay? This goes until infinity. There is a pipe. This is X. Okay? So this is the surface. If this surface temperature is specified, you use this. If on this surface the heat flux is specified, you use this formula. If on this surface there is a convection, constant convection. Okay? Convection on the surface. Convection on the surface due to wind or water, whatever. You use this formula. They are asking you temperature at some point here, this pipe here. Okay, that is Txt. Ti, in this case, let's say this is soil. So Ti is the temperature of the soil. T infinity is the temperature here of the air. ERFC is the error function. It's given in the table. Physical meaning I will explain. Okay. Then again there is a big term which becomes 0 most of the time. Okay, so you see it in your book. Case 4 is energy pulse. Okay, energy pulse EE is constant. Energy pulse is heat is given in pulses. Let's suppose this is skin. This is skin. And this is tattoo laser. The laser that you use for tattoos. It is pulsed for few seconds, microseconds, right? So in that case, if the numerical is saying the energy is given in pulses, then you use this equation.
มันจะออกตัวสุดท้ายเลยนี่ออกให้ครู
เลยกี่ตัว
We will do numericals on these cases, then you will understand better.
ไม่มีแต่สีแล้ว
Okay. Semi-infinite solid, you will have 4 cases. All numericals based on 4 cases. Either your temperature is given, surface temperature is given, heat flux is given on the surface. Semi-infinite solid are like this. They are extended in infinity direction. Okay. This is an example of an earth. In the earth there is a pipe. Alright. They are asking you, let's suppose what is the temperature at 2 meters, 2 centimeters. Right. Ti is the temperature of the soil, for example. Ts is the temperature of the surface, and this is given. So I will use this formula. Right. And they are probably asking me this. This I will get from a table. Alright. Specified heat flux. If I am giving some sort of heat here, okay, I have a heater or I'm giving heat, okay, on the surface, and they are asking the temperature here, somewhere here. So I will use this formula. Okay, this is Ti, maybe soil, maybe skin, whatever. This is very big, but most of the time, like I said, this becomes 0. Okay. Convection of the surface, again, it's a soil. Flowing like hot water, let's suppose, right? And the heat is transferred, it's like penetrating here. I will use this formula. They are asking me temperature after 2 centimeter, 3 centimeter. Energy pulse, if I have a laser or something, right? The energy is given in pulses, in microseconds. And then they are asking me something here. Okay? Then I will
โทรศัพท์แล้วก็เอาที่ใส่กลับบ้าน
ฮะ
ก็มีคนมากลับบ้าน
เกิดดำเลย
อืม
ดำยังไงนี่วะ
So they have given a convection heat transfer coefficient. Okay? And then they are asking temperature at this distance, this distance, this distance, this distance. The convection on the surface formula is very big, but I will show you how it becomes zero. Most of the part becomes zero. Okay?
รอยตรงไหนไม่สวย มีเก็บอะไรเล่นเลยมีเป็นเพื่อนไม่เห็นมีเก็บอะไรเล่นเลยไม่เห็นมีเกมอะไรเล่นเลย
The soil temperature in the upper layer of the earth varies with the variation in the atmospheric condition. Before a cold front moves in, the earth at a location is initially at a uniform temperature of 10 degrees Celsius. Okay. Area is subjected to a temperature of minus 10 degrees Celsius high wind that result in a convection heat transfer coefficient. Case 3. Okay. On the earth's surface for a period of 10 hours, taking the properties of the soil at the location to be this, determine the soil temperature at distance this. I will write down the full formula for case 3. So they are asking this at x different 0, 10, 20, 50 centimeter. Okay, they are asking this. These formulas you write down in your A4 paper. I will show you the these are the cases and the error function then you will see this becomes 0. This is in multiplication of this becomes 0. I will tell you how. Okay. So, alright. Okay. The eta value is 30.36, very high, right? At 3.60 it becomes 0. At 0 it's 1. Starting from there, if my eta value comes 0, right? The ERFC and in bracket eta will be 1, topmost, right? As it increases from 0, as it increases, it reaches 3.60 and this becomes 0. In my case, this is very high. It is already 30.36, right? So this thing is definitely 0. It should be less than maybe 2 to get some significant value. As this eta value is increasing, this value becomes 0. Okay, this is the thing. So if I add these two, no need to add. This is already very high. This is already very high. So this is 0. Okay. So I will write down here ERFC eta should be less than 3.60. Okay. Since from our calculation we have 30.36, so this ERFC and 30.36 plus 4.3214, this whole thing becomes 0. This is 0, this is 0, this is 0, we have only this. I will only solve for this from here to here. I have this this one here. Okay. So I will solve for this. The board is not enough. So I will only write this. I will only solve for this, right? Because this term becomes 0. From the table we see that this is greater than 3.36, 3.60. So it's 0. Okay? So I will only solve for this. So I'm trying to find out this at 0.5, right? 0.5, 10 hours. T infinity is minus 10. Temperature inside is 10. Okay. Okay, now this value. solve this,
ใช่
you get temperature at 0.5 meters
อันเนี้ย
for 10 hours equals to minus 30 degrees Celsius. Okay? First you read the question very carefully. See which case you can apply. You have 4 cases. Okay? You don't have what? No. It's object related. Yes.
เพราะอะไร
ถามว่าหมายถึงว่าเพื่อนถามว่ามีคำว่าอะไร
รู้ละ
บอกด้วยเพื่อนถามคำว่าอะไร
อันนี้คือเขียนมาแล้ว
ไหนถามว่า
เนี่ย
ภาษาอังกฤษอะไร
เออ
บอกว่าจากการคำนวณแล้วถ้าเห็น
ไม่แล้วหน้ามันเลยอะไรหน้ามันเลยปะ
มันเป็นสูตรไอตัว e อะไรแล้วกัน
ไหน
ชี้มันเป็นสูตรจริง
ไหน